Okay, so we're going to talk about the Coulomb, not the man, although there was a man. We're going to talk about the unit of measure, Coulomb. And you've seen it before because it is part of the electricity unit that you take in grade 9. Okay, so it's a unit of measure of charge. Okay, and okay, the Coulomb is a unit of measure of charge. So we're going to do a little bit of a recall here. So recall that an atom has a positive nucleus in the center, surrounded by negative charge. Okay, this is a very simple version. Okay, um, and that the negative charge is carried by electrons, and the positive charge by protons in the nucleus. There are also neutrons in there, but we're not interested in those because they don't actually carry a charge. They're neutral, hence neutron. Now, electrons carry and protons carry a very small amount of charge. Okay, and what that charge is called it's called the elementary charge. When we write it as E negative, we mean negative elementary charge. When we write it as E positive, we mean a positive amount of that charge. Okay, and it turns out that charge is measured in coulombs, and we'll talk about what charge means in just a minute, but say that 1 coulomb is the equivalent amount of charge that you would find in 6.24 times 10 to the 18 electrons or protons. Okay, so it's the amount of charge carried by that much. So in other words, the value of this is simply the inverse of that. If you need 6.24 times 10 to the 18 electrons or protons to carry 1 coulomb, and the amount that each of these would have, the amount of charge each of these would have, equal to that value, which is 1.6 times 10 to the negative 19 coulombs. So the elementary charge then is equal to this value. All right? 1.6 times 10 to the negative 19 coulombs. That is the amount of charge carried by a single proton or a single electron. All right? Protons carry a positive amount of this. Electrons carry a negative amount of this. It's exactly that amount. And all electrons and all protons are identical to each other. Okay? So we're going to talk about electric fields, but coulombs are definitely used in current electricity. In fact, the unit, let's give a little background. The unit of the amp, which is the fundamental unit, well, an amp delivers 1 coulomb of electric charge every 1 second. Okay? So the amp is 1 coulomb per second. So it's that amount of charge traveling per second. Okay? So that's kind of where amp and coulomb are related to each other. If you've ever heard of a 15 amp fuse, well, that's a fuse that would blow if more than 15 coulombs were passing through it every second. Okay? All right. Because the amount of charge carried on an electron or a proton is very small, the coulomb ends up being quite a large unit. And we'll talk about how large in a minute or two here. So let's bring in the concept of electric fields. This is a very kind of similar topic to gravitational fields like we talked about before, except now there's, now they're based on the amount of charge rather than the amount of mass, and they can be either positive or negative. They are attractive or repulsive. So let's say I have a sphere, and on this sphere I have like a 10 coulomb charge, let's say. No, let's not even say that. Let's just say a positive charge. I want to talk about how something would get a positive charge first. Okay, so if we remember, all matter is made of atoms, and all atoms have positive and negative charge in them, right? And it turns out that you can add and subtract amounts of charge from objects, okay? There's lots of different ways to do this, but if you've ever taken a unit on static electricity, you kind of know what some of those are. One might be friction, one might be induction, conduction, etc. But there's ways to remove charge from here. So if I start to take charge out, say I take 4 electrons out of here, my previously balanced charge is no longer balanced, and I'm left with an overall charge of +4. Does that make sense? Now, you can't remove the positive charges because they're in the nucleuses of atoms, but you could add negative charge to this to make it negatively charged. So the amount of protons in here, the amount of nuclei, is sort of set by the substance, and by adding or removing, we can charge this object. Okay? Now, it turns out that if we have a charged object, we can detect a field around it. You may have noticed this if you've ever taken a balloon, rubbed it on your head, and found that it sticks to the wall or makes your hair stick up. The reason why is because it has exchanged some electrons with your hair. Whatever it is rubbed on becomes negative, and and it becomes positive as the electrons are lost to it. Okay, so this is the kind of thing we're talking about. Now you can take this balloon and it'll stick to the wall. We'll talk about why that is in a little bit. If I want to measure the electric field around a charged object, I do that with a positive test charge. So a positive test charge is just a little mini charge, and I move it around the area where this field is. Now think about it. Wherever I put this test charge, it's going to feel a repulsive force. Okay? Like charges repel, opposite charges attract. So a test charge to test a field is always going to be positive. So in other words, what I'm drawing here is what the test charge would feel in terms of force if I were to put it in any position around this large positively charged sphere. It would be propelled away. It would feel an outward force away from that object. It would be repelled. And conversely, if I took a negative object and I took the positive test charge and I placed it, it would feel an inward, or a force towards. So what these lines represent is just the force field, right? Just like with gravity, where it always pointed in, a mass is always attracted to the center of any other mass. With electricity, it's very similar, except it can be repulsive or attractive, okay? And we use a positive test charge to measure fields, okay? Because the test charge is positive, and why is it positive? It's a rule of thumb. It's the way it is. It's based on a positive test charge. Because it's positive, then by that ruling, we would always draw charge out of positive and into negative, okay? And the last thing I want to show you before we kind of wrap up is just what would happen if we had a positive near a negative, okay? Now you can imagine if I put my test charge right in the middle, there'd be an attractive force directly this way. If I put it here, it would kind of be repulsed a bit from here, but also slightly attracted by here. You can imagine if I moved it to here, it would be repulsed there and attracted there, which would cancel out in terms of the vector. And so what we get is we get this kind of a shape developing, where if you imagine the pull and push of the test charge, depending where I put it, you're going to get a field that kind of gets drawn like this. Okay, remember, what this is showing you is if I were to take my positive test charge and place it here, the resultant force it would feel would be in that direction. If I were to put it here, it would be attracted towards. If I were to put it here, it would be repulsed away. The reason this has a curve to it, though, is because as I get farther from here or more over to here, the negative charge starts to pull it towards, and you get this shape.